All right, good morning, ladies and gentlemen. It is Monday, February the 8th. This is ICP, and we are going to be talking today about energy. Okay. So we can now talk about whether or not an object is moving. We can talk about its distance versus displacement. We can talk about differences in its speed versus velocity. We can calculate its acceleration. But guys, none of that motion can actually happen without the object using energy. And that's what we're going to focus on today. How do objects use, store, and transfer energy? So there's two kinds. We're going to be talking about kinetic. Let me go ahead and share my screen here so we can see this. We are working out of day 8. Let me share the screen. Share screen. Screen 2. There we go. Okay, so we are in ICP. We're working on day 8. We're going to start working with the energy notes. I'm just going through this stuff real quickly with you guys. We're first going to take the notes. That's the PowerPoint. This is the fill in the blanks. At the end of the notes, we're going to watch a tiny little video on from BrainPop on just reviewing the topics we talk about today. And then here's the practice. After you get all this done, go ahead and submit this, and then make sure you jump down and fill out the next ticket as well. Okay. But let's get into potential and kinetic energy. Okay, so today we're talking again about potential and kinetic energy, and they're actually being illustrated in these two pictures, but we'll talk about how that works here in just a moment. So first off, we really have to talk about what is energy. How does energy work? Well, energy is simply defined as the ability of an object to do work. Now, everything that happens in the world uses energy. The key is that it's being used. We just don't often see it being used. Sometimes we can, sometimes it's easy to see that energy being put to use. However, most of the time we don't really consider all the energy being used anytime an object moves. Now here's the key. And guys, this is the most important part about energy. Energy is never created or destroyed. Okay, that is a rule. You cannot create energy out of nowhere, and just because you have extra energy, you can't make it disappear just because you want it to. The energy can only be stored or transferred to another form. Okay, so energy that might appear to disappear might just be that it's going into being stored and it's going to be used later. Or it might be turned into a different form of energy that we don't necessarily think about, aka it could be heat or it could be light. So that's the key. Energy is never created or destroyed, only stored or transferred. You might hear me say transformed. Either word works. All right, so batteries. Batteries are an example of ways that we store energy for later use. These batteries are not so much, in everyday life, but you definitely use the battery on your cell phone. And what do you have to do? You charge that, over the night or at night so that you have a phone charge to be using all day. That energy is stored in the battery, and then that energy is transformed later to make your phone. Cars use lots of energy, all right? Their gas is a form of stored energy. So you put gas in your car, that car then takes that gas, lights it on fire, so it's actually changing that chemical energy into heat and light, combustion, right? So that's actually going to move the car, push the engine parts to move the car. So lots of energy transformations going on inside of a car. When you think about things like us, living things, we need energy as well. We're not exempt from this, and we get our energy from eating food. So food has energy stored in the chemical bonds of the atoms. And when you digest that food, you break it apart down into things like sugar and glucose, right? And then your body's eventually going to take that glucose, break it apart, and use it for energy to power your muscles and all of that. So we also have to get energy in order to do work. And it's important to understand everything's constantly using energy, pretty much, unless it's just, sitting on something and stored. Everything has energy. Even when you're sleeping, you're actually using a lot of energy. So constantly using energy to carry out your life processes. Nothing happens without energy. That's the key. Now, we're going to get more into this later, but for right now, We're not really going to talk about all the atoms and stuff. Just think everything is made up of particles. We'll eventually name them atoms, but right now, everything's just made up of these little bits. And the key is these atoms, these particles, are never not moving. What does that mean? That means everything from solids, liquids, gases, everything that has atoms, all those atoms are in motion. And that means that they're using energy. That's the key. Now, all of that energy can fall into one of two types. Either potential energy, right here, potential energy, or kinetic energy. Now, on your notes, guys, this is, horizontal versus vertical, so just make sure you add those to the lines. But the two types of energy we're going to be talking about are potential energy and kinetic energy. So first, let's talk about potential. What is potential energy? Well, potential energy is the stored energy in an object. Now, what does that mean? What does it mean to be stored energy? Well, we're going to be talking about that it's stored and it has the ability to do something useful later on. That's what I mean by stored energy. It's going to keep that. It's not going to do something at the moment. It's going to be doing that, using that energy later on. Now, in this class, we're going to focus mostly on the potential energy due to gravity, so how high off the ground something is. We're not going to focus so much on that chemical potential energy. That would be in, more of a biophysics class or something like that. But the key here is that we're focusing on energy of a stored object, stored in an object due to its position, how high off the ground it is. But let's talk about all the examples of potential energy. If you stretch a rubber band, you're giving it that energy, right? And it's stored. And once you let it go, boom, it flies. It does something. Okay, so while it's stretched, it has lots of potential energy to do something. The water at the top of the waterfall has potential energy because what happens as it moves over the edge? Well, then it falls and it starts to use that energy. But while it's at the top of the waterfall, it has lots more potential energy than at the bottom of the waterfall. A yo-yo is another example. While it's in your hand, it has lots of potential energy, and then you release it, and it uses that energy. And then if you pull back on a bow, that's another thing of potential energy. The arrow's not going to move until you let go of that string, right? But as you pull the string back, you're basically adding potential energy into the bow. And while you hold it there, it's just got that potential until you let it go, and then the arrow flies. So what are the two factors that affect how much potential energy an object has? Well, there's two main things. The higher an object is, the more potential energy it has. Also, the more mass an object has, the more potential energy it has. So what does that mean? Well, let's say, and here we go with the bad penmanship. I'm just going to draw a circle. All right, let's say I had a ball here, all right, on the ground. All right, there's our ball one. And then I had the same ball, the same mass, and I put it, let's say, let's draw, it's a little shelf. We're going to put this ball on top of the shelf. Now let's pretend that these two balls have the same exact mass. Okay, so they're the same size, same mass, but one is higher up than the other. This applies to this first part. The higher an object is, the more potential energy it has. So this ball at the top on the shelf has more potential energy than the one down here on the ground. Right? And again, it's because all that energy of the height is going to be used if it were to be knocked off. Now, if we had another ball also on the shelf, let me change color here. Let's say this ball had twice the mass. Pretend that's twice. All right, you guys get the idea. We had a much larger one. Actually, let me clean that up a little bit. If we had a much larger ball, I'm just going to draw. That's better. Okay. So if we had these two on the same shelf, now they're at the same height, but they're of different masses. So that means that the blue one is going to have more potential energy. Why? Well, because it probably took more energy to put that one up on the shelf than the other one. So therefore, it has more potential energy to use. Okay, so the blue one has more than the red one when they're at the same height, But between the two red ones, the higher it is, the more potential energy it has. So this is how you can think about the two factors of potential energy: height and mass. Okay. So what can we do with that? Well, we can take that and guess what? We can turn it into a formula. That's exactly what we are going to do. We're going to be adding a new formula to our repertoire, formula to calculate potential energy. So it's really about its position and its weight. But remember, we have to define weight as the mass times the gravity. So we're going to be using this formula. Circle it right here. Okay. So how do I read this? Well, it says potential energy equals the mass of the object times its gravity times its height. It's very simple. Couldn't be easier. Straight multiplication. Mass times gravity times height. Now again, they're not always just going to give you those three and ask you to solve for potential energy. The key here is that as long as you have 3 out of the 4 of these variables, you can always solve for the other one. So again, the shorthand way to write this is PE equals mgh, mass times gravity times height. The mass has to be in kilograms. It's important to note. Gravity on Earth is always 9.8 meters per second squared, right? That's the acceleration due to gravity. Hey, second squared acceleration, right? And then h is just the height, and that'll probably be in meters. Now, the key here is the metric system unit for energy is just called the joule. We measure it in joules of energy, that capital J right there. It really stands for kilograms times meters squared over seconds squared, which is why we just kind of combine it like we did with the Newton stuff. Remember, we just took all those units from Newtons and just made it Newtons. We're going to take all these, jumble them together, and just call it the joule, 1 joule of energy. So let's see if we can put this into practice. Which of these two objects has more potential energy, assuming they're at the same exact height? We have a brick, we have a leaf. Which one has more potential energy? Hey, I'm going to assume that you got it correct. It is the brick. Why is the brick having more potential energy? Because it has more mass than the feather. All right, more mass, more potential energy. Now, let's say we took an object and we dropped it from the top of each of these 3 objects. When, let's say we're going to drop an apple, when is it going to have the most potential energy? Top of the skyscraper, at the top of the chair, or off the top of the crane? Which of these 3 was going to have the apple going to have the most potential energy? Well, hopefully you selected answer A. Why? Because the skyscraper has a much bigger height, right? The apple's mass isn't going to change, but the height does. Therefore, the highest point, the most potential energy. That's simple. Mass times gravity times height. Now, here's the key. We said earlier, energy can never be created or destroyed. So as the apple is dropped off of this building, we know the height is decreasing. And if the height is decreasing, that means the potential energy is decreasing. But remember what I just said, energy cannot be created or destroyed. So as that apple falls and its potential energy is decreasing, right? If it's halfway down, it's half the potential energy from the top. The key here is that it's not being destroyed, it's going somewhere. And that's because of the relationship between potential and kinetic energy. When the stored energy of an object begins to move, we are then transferring from potential energy into kinetic energy. So as potential energy goes down, kinetic energy is actually going to start to increase. So again, we're not creating or destroying it. We're taking that potential and we are turning it into motion, into kinetic energy. Never created nor destroyed. It has to come from somewhere and it has to go somewhere. So how do we define kinetic energy? Well, as you kind of maybe were able to infer, kinetic energy is the energy of a moving object. That's because kinetic means movement. All right, kinesis, movement. When stored energy is being used up, it's making things move or happen. So again, this is talking about the transfer of energy. It's going to go from that potential energy into kinetic energy. So what are some examples of kinetic energy? Well, if you're skiing down a hill, you're in motion. Therefore, you have kinetic energy. Even if you're running on a flat road, you're in motion. You have kinetic energy. You're on a motorcycle, moving fast. Lots of kinetic energy. And as some of you may have found out, over this weekend with the snow that we're about to get again, if you slip on ice and you fall, that falling motion is kinetic energy. Okay, you're going to hit the ground with some force because you're really turning in your potential of standing upright into, falling, and that's a transfer from potential to kinetic energy. So there were two factors that affect potential energy. Remember, the height of the object and the mass. There are also two factors that affect the kinetic energy of an object. The first is speed. The faster the object moves, the more kinetic energy is produced. So if a cheetah is running and I am running, the cheetah is much faster than I am, believe it or not. Therefore, it's going to have a much greater kinetic energy. Now, just like potential, also the mass matters. The greater the mass and speed of an object, the more kinetic energy it will be. So if I have two objects traveling at the same speed, but one has more mass, it's going to have a greater kinetic energy. If for some reason the cheetah and I were running at the same exact speed, a little bit bigger than the cheetah, I have more mass, therefore it took me more energy to get up to that speed, therefore I have more kinetic energy. So let's put this into a formula. Now I'm going to warn you guys, this formula is a little bit different than the other ones we've been dealing with, and I'll point out why here in a second. So when I need to figure out an object's kinetic energy, I need to take 1/2 times the mass times the velocity squared. And I cannot emphasize that enough. This is so important. The order of operations says that you have to do this part first. You have to take whatever that speed is, right? The velocity, you need to multiply it by itself. You need to square it. So again, the kinetic energy of an object equals 1/2 times the mass times velocity squared. So if I were doing this on a calculator, I would take whatever the velocity is, multiply it by itself, then times it by the mass, then times it by 0.5. So again, this one's going to be tricky. It's also going to make it very tricky when we need to find out the velocity. If they give us the kinetic energy and they give us the mass, but they don't give us this velocity, this is going to be a little bit tricky to solve for it. We're going to talk a lot about how to do that one correctly. All right, so if we had a tractor trailer and a little smart car and they were traveling at the same speed, which one of these has more kinetic energy? Well, if you answered the semi-truck, you are correct. That's not the right direction. There we go. If you answered the semi-truck, you are correct. Because why? Well, if they're traveling at the same speed, the semi has more mass. Therefore, it took more energy to speed up, more kinetic energy. Now, an object has the most kinetic energy when its movement is the greatest. The faster an object is going, right, the more kinetic energy it has. It's going to have the most when its speed is as high as it can get. Now here's the key. An object has the least potential energy when it has the most kinetic. This is an inverse relationship. Now what does inverse mean? Well, inverse means as one goes up, the other goes down. So as the KE, kinetic energy, increases, that's because the potential energy is decreasing. Or we could swap these two. As potential energy increases, then kinetic energy goes down. Okay, inverse. One goes up, other goes down. So keeping that in mind, let's look at this example. If a water bottle is knocked off of a desk, when does it have the most kinetic energy? Is it A, at the very top of the fall, B, in the middle of the fall, or C, at the bottom of the fall? And again, this is asking, when does it have the most kinetic energy, energy of movement? So if it's at the top of the fall, it's not moving very fast. We can eliminate that one. It's not the top. That leaves us, is it at the middle or is it the bottom? This is a little bit tricky. Technically, it is C, at the bottom of the fall. The instant before the water ball hits the ground, it has the greatest speed, and therefore it has the most kinetic energy. It's had the longest amount of time to speed up, and that's really the key. At the top of the fall, it's moving slower, and then it speeds up. Halfway down, potential and kinetic should be equal, right? Because if it's 100% potential at the top and 0 at the bottom, right, as they go down, they transfer. So halfway down, it's going to be even. Then the instant before that water ball hits the ground, it's had the longest time to speed up. It's moving the fastest. The instant before it hits the ground, it has the most kinetic energy. Also, you can remember it has the least potential because it's barely above the ground or just touching the ground. So that potential is dropped to nearly 0. All right, that's it for the guided notes. What we are going to do now is we're going to transition over to the BrainPop. Okay, again, let me pull up the classroom information because I want to point you guys to where the website is. So hopefully I believe you guys can see my second screen. But in this case, if you guys look at number 2, there's a little link there. We're going to click on that link. It's going to take us to BrainPop. It's going to take us right to the video. And when you go to play it, it's going to ask you to sign in. Again, the username is BaltCops, BALTCOPS, and the password you're going to use is one word, lowercase, BrainPop, BRAINPOP, and that will get you logged in so that you can view the video. But if you're watching with me, you don't need to view it on your own. So, or you can if you want to be able to pause it when you want to. But we're going to go ahead and watch this right now. Sorry, I should pause and say that what you guys are going to be answering with this comes from, let's minimize this. Hold on to Moby. All right, it's this worksheet right here. It says print PDF, but you guys can answer this on a worksheet if you want, or just attach it, or just email me the letters and numbers. It doesn't matter, whatever works easiest for you. Okay, now back to Moby. All right, guys. So that's just a quick little video. I know a lot of information very quickly. So if you need to watch it again, go ahead and replay that. We're not going to do it on the Zoom call, though. Just take a moment, pause this, and answer the questions on the PDF. Again, you can do it on a separate sheet of paper or just email it to me. It's up to you. Number and letter would be good enough. All right, I'm going to assume that you've done that now. The last thing you have to do in terms of the practice is the kinetic and potential energy practice. I'm just going to pull this up so we can go over it. What we have here at the very top, you just need to classify it. Is it K or P? Kinetic or potential? Remember, kinetic is in motion, potential is stored. Then it's going to ask you to think of some examples around your house. Do the best you can with this. Just come up with something that has potential or kinetic energy. Give me an example of each. And then down here, they have given you some of the problems. Now, I would like to work through a couple of these as examples. The top I'm not going to go over. That's very basic, very simple stuff. But I'm going to go through a couple of these with you to make sure that you know how to complete the actual practice in terms of doing the problems. So let me pull up the camera, grab some paper. Okay. Stop sharing my screen because I think it will be bigger. Oh, hi, Hannah. Sorry, I didn't see you jump in there. I'm just recording the video for today. It'll be posted so you can go back and get the stuff that you missed, all right? All right, so I'm gonna share my video. There we are. So again, what I'm going to be going over is just some of the questions from the practice, okay? And I'm going to start by going over, let's do number 15. All right, number 15 says, determine the kinetic energy of a 1,000 kilogram roller coaster that is moving with a speed of 20 meters per second. Okay, so again, we have kinetic energy. So the first thing I'm going to do is write my formula. So we have KE equals 1/2 times the mass times the velocity squared. And this is the key. We're going to have to do this one first. So now I plug in my numbers. 1/2 stays as 1/2 or 0.5. Because I write 1/2. If you want to write 0.5, that's how you're going to put in the calculator anyway. Doesn't matter to me. Times the mass. We said the mass was 1,000. Okay. Again, I could put the units in here, but I'm not going to just because at the end, I'm just going to slap on that J for joules. So I'm not going to put the units in here. Just make sure they are in the correct units. Times the velocity squared. Now the velocity is 20 meters per second. So 20 squared. Now the key is I have to, order of operations says I have to do the exponents first. So what I'm going to do is I'm going to just simply take in my calculator 20 squared, which is just 20 times 20. And that's going to give me an answer of 400. So just rewrite this. So we have 1/2 now. Sorry, this is getting tilted. There we go. 1/2 equal, or times 1,000 times 400. Now, we all have multiplication here, so it doesn't matter what order we do this in. So if you still have 400 in your calculator, that's fine. Multiply it by 1,000, so times 1,000, and then times 0.5. And what you should end up with is an answer of 200,000 joules. Okay, let's put that J on there for joules. And guys, you're going to get some big numbers for kinetic energy. Objects can have a lot of kinetic energy, and that's just perfectly fine. Okay, so again, 1/2 times the mass times velocity squared. I have to do this part first. All right, so I plug in my numbers. That gave me 400. Now it's straight multiplication. Gives me 200,000 joules. Okay, let's take a look at the question. Let's do a potential energy one. we're going to skip over 16, just double the speed for that one, guys, right? It says double the speed, so instead of 20, you should be at 40. And let's do not number 17, because that's going to give us, let's do number 19. Jump down to number 19. I'm going to try and straighten this out. Struggles are real today with the camera. There we go. All right. All right, number 19, this is what it says. It says a 75 kilogram refrigerator is located on the 70th floor, aka 300 meters above the ground. What is the potential energy of the refrigerator? So first thing I have to do is write the formula. So potential energy is mass times gravity times height. Now there's 3 variables there, but they only gave us 2 numbers. And this is the key, guys. They are not going to tell you gravity, because gravity is always 9.8. So gravity equals 9.8. That's not going to change. They're not going to tell you the gravity. You have to remember gravity 9.8. I believe that is on the formula card. So now I plug in my numbers. My refrigerator was 75 kilograms. So 75 times my force of gravity, which is always 9.8, not told to me in the problem, times the height. The height is simply 300 meters. Now this is straight multiplication, so it doesn't matter what direction I do it in, but I'm going to bring up my calculator. I'm going to take 75 times 9.8 times 300. And what do I get? I get an answer of 220,500. Double check that just to be 100% sure. I didn't hit a button wrong. 8 times 300. Yep, that's the answer I get twice. So what's the unit? The unit is joules. So just put that J there for you. Okay. All right. I would like to do one where you have to solve for another one. Let's go back up to number 17. Number 17 is a little bit tricky, so I do want to take some time to talk about this one together. All right, number 17 says, Missy Dyewater, the platform diver for the Ringling Brothers Circus, has a kinetic energy. So they're giving us the kinetic energy, a kinetic energy of 15,000 joules just prior to hitting the bucket of water. If Misty's mass is 50 kilograms, then what is her speed? So this is asking us to calculate what is her speed the instant before she hits the water diving off of this high dive. So here's the key. Same exact formula. We're not going to rearrange this one at all. So we're talking about kinetic energy. So KE equals 1/2 times the mass times velocity squared. But the thing is, guys, is they gave us the kinetic energy. Remember, that is 15,000 joules. So I'm going to put 15,000 equals 1/2 is just going to stay as 1/2. We said Missy's mass was 50 kilograms, and we don't know her speed. So we're just going to leave v squared by itself. And this squared part is going to make this just a little tricky. And this is why we're going over this one. So I'm going to combine like terms here. I've got 1/2 and I've got 50. So 1/2 times 50 is simply 25. So I have 25v squared equals 15,000. Just combine what I could on this side, right? Now, what's happening between the 25 and the v? Well, that's multiplication. How do I undo multiplication? I need to divide. Sorry, I don't know why I'm writing it at such an angle today, but I am. So I'm going to divide both sides by 25. So in my calculator, I'm going to take 15,000 divided by 25. And that's going to give me an answer of 600 equals v squared. Now, am I done? Well, technically, oh, sorry, you guys can't see that. Technically, no, I'm not finished. Why am I not finished? Well, I'm not finished because I need to solve for v, not v squared. So I have to undo this squared. Now, this is the tricky one. Remember, the opposite of addition is subtraction. The opposite of subtraction is addition, right? The opposite of multiplication is division. The opposite of division is multiplication. So how do I undo a squared or an exponent? Well, I actually need to take the square root of both sides. And this is what makes this one so tricky. I actually have to take the square root of both sides. So the square root of v squared is just v, which is what we're solving for. Okay. Now, in your calculator, the key here, guys, is that you have to put in the number or the square root sign first. I can't tell you which way your calculator works without knowing what type of calculator you have. So you just need to pay attention. Sometimes if you're using the normal, function calculators, you need to hit the second button and then hit the x squared. That's what I tell my students to do on their calculators. And let me actually grab one so I can show you what I'm talking about. Okay, so here we've got these calculators. All right, very simple. You should recognize this type. But when it's on, okay, if you look right here, okay, this little x squared button, in blue behind it is the square root symbol. Now it's a little hard to see. I don't think you guys can really see that very well, but there's a little square root symbol there. So what I have to do is I have to hit the second key, then hit the square root key. And if you see, it gives me a little number, a square root sign in a little parentheses. Then I would put in my number of 600. And I can end the parentheses if I want. And then I hit the equal sign. And then we end up with an answer of 24.49, which I'm just going to round up to 24.5. So we have a speed of 24.5 meters per second. And now, guys, that is Missy's speed. Now I've done all the steps and I've gotten to the correct answer. And look at that. Look at how curved that is. That's crazy. Okay, well, it's happy Monday, everyone. Is that easier or harder to see? There we go. All right. Solving for one of the potential energy variables is far, far easier. So we're not going to go over examples of that. This one was just a little tricky because you had to take the square root at the very end. Everything else is just very simple and straightforward. If you guys do have questions or comments, just don't hesitate, email me. All right, we can set up a time to Zoom or things like that. So it is very important, guys, that you're following along, completing the work. Remember, just a reminder, the test from Thursday of last week is open. I would really like it done by this Thursday. So you need to get into the building, get with your coach, make sure that you set up a time and you can come into the building and take that test. And I don't know if you guys saw, let me go back to sharing my screen real quick. Share screen 2. All right, so I don't know if you guys saw, discard those. And pull up the Google Classroom again. I made a little announcement on the announcements, but under the class videos, so they should be on top. So they're always on top. I did, guys, add in a review video here. So week 1 and 2, it's very quick. It just goes over all the topics super fast. I just kind of did it on spur of the moment because I thought it might be good for us to talk about this. I would normally review with you guys before a test anyway. So there's a little review video there for you to go through and follow along with that to review. But also this video will be here later for those of you that need it. So get your test done. All right, I did put an announcement in there. So there's one here. There's also one a little bit earlier, guys. So I've been trying to get this out to you. I don't know the best way to reach out to everyone, but I've just been leaving little announcements in the class. So make sure you're following along with those. Other than that, guys, that's all we have for today. Once you are finished with the practice, submit that, the notes and practice, submit that for points, and then you have the next ticket right here. All right. Like I said, reach out if you have questions or concerns. Tomorrow, we're going to be focusing a little bit more on, or continuing to talk about kinetic and potential energy and how they work together. All right, guys, I will see you tomorrow.